I'm Jonny Huck. I'm from MCGIS at the University of Manchester, and I'm looking at empirical agent-based modelling of intergroup contact in a segregated city, because I like a good snappy title for a presentation. So there we go. Unlike David, I'm afraid that I don't have any results to show today because of COVID. We've been having to do lots of other things at the university, so I don't have any results, but what I do have is hopefully quite an interesting discussion around empirical agent-based modelling, and particularly the way that we're applying it in this project. The project itself is called the Belfast Mobility Project. This is a multidisciplinary project that we set up quite a long time ago. It began in about 2015 and ran to about 2018. But we're still analysing data, writing papers and so on into this day. It's a team of psychologists, sociologists, geographers and others that were looking to explore the interplay between segregation and mobility in northern Belfast. This is the region of Belfast and Northern Ireland that's probably seen the least integration since the Good Friday Agreement in 1998. The majority of people in this area are still living in segregated communities of Catholics or Protestants, separated in many cases by peace walls, like the one you can see in the picture there, that's just cutting a road straight in half to keep two communities apart. This is also the part of Northern Ireland where a lot of the violence you've seen in the news, if you're in the UK, over the last couple of weeks has taken place. So since the 30th of March, there's been daily violence happening as a response to the implications of Brexit, some political issues around the attendance at a funeral, and several other things that have been going on. And there's a lot of violence going on, and a lot of that, certainly the worst of it, is happening in this place as well. So it's a very timely moment for us to come back to this area and have a look again at some of the data we've got. What I'm looking at today really is a psychological theory. It's called the contact hypothesis. And this is an idea that originated with a psychologist called Gordon Allport in the 1950s. And there's been a lot of research on that in the 70 years since. It's quite straightforward, really. It's the idea that contact between social groups is effective in reducing prejudice. So we're saying that if you have groups that are prejudiced, that are segregated, creating contact between them effectively should reduce that. And this has been shown a lot. As I said, there's been a lot of studies. In 2006, there was a study of more than 500 empirical studies about the contact hypothesis. And this is a review of those. It shows that the Pearson's R value, if you're mathematically minded, or the relationship between them, if you're not, is negative 0.21. So that's effectively saying there's a medium to low negative relationship between levels of contact and levels of prejudice between communities. And this is something that's consistent. So this number, you can see it's relatively tightly distributed around that, particularly if you've got higher numbers of participants, which is on the y-axis there. And that's consistent across different populations, different parts of the world, different contact experiences, intergroup settings, and so on. And the other interesting things that people have found is that the more meaningful the relationship, so if it's a friend or it's a partner, then that increases a bit. It gets to more like 0.25, which means it's a stronger relationship. And also that people who are less tolerant or more prejudiced have a greater effect. Contact has a bigger effect on them, which is quite useful, because it means that the most prejudiced people can be most easily targeted by measures to increase contact between conflicted groups. It isn't, of course, that simple. It is, a very complex problem, and a big issue is that there are different types of contact. If you were to get beaten up by someone in an opposite group, I don't think that would help reduce prejudice. So we have to be able to distinguish between positive and negative contact. And negative contacts are more of a recent thing that people have been looking at in psychology. There's not as much research on that. So we don't have clear studies like we do for the positive contact, but what we can say is that negative contact happens much less frequently, but has a much greater impact on attitudes. So we do understand the patterns, even if we don't have the data to model them accurately just yet. The interesting thing here is that even though I've shown you, more than 500 studies over 70 years, there really isn't any understanding yet. There are really big shortcomings in our understanding of how we can apply contact as a tool for social change. So while we understand that groups having contact between each other are able to, address their issues and reduce levels of prejudice, what we're not seeing is people using this as a way of promoting harmony and reducing conflict by creating opportunities for contact. People have tried to do that, but there's not really a great understanding about how it works. And that is what I want to do here. I want to use a simulation-based approach in order to evaluate the outcomes of various interventions that we could do to try and promote contact and therefore the reduction of prejudice. We can understand things like what expected impacts might be of an activity we do before we actually do it, which is a classic use of simulation and modelling. And what targets we need to make for any interventions. Crucially, is there some kind of tipping point if we can get to a level of reduced prejudice after which it starts to dissipate and these cycles of violence and cycles of threat disappear. So that's what I'm really interested in here. And it hasn't been done before, as I said, and a big part of that is really because it poses quite a big modelling challenge. The phenomena we're dealing with here are very, very complicated. Human decision-making, human behaviour, interaction, mobility, these are very complex, very dynamic things. And, modelling any one of these is a big task for an agent-based modeller. There's a lot of psychological theory there, and there'd be too many assumptions. It builds up too much for me. So what I'm interested in is how we can do this in quite an empirical way. So I've been looking at a way of making a rather abstract approach to mapping human behaviour in the context of northern Belfast in order to be able to test some of the psychological theories around contact and prejudice. To be able to do that, the thing that's enabling me to do that really is this assumption. So I'm making one big assumption in this work. And this is something that really is borne out by the work we've been doing there over the last 6 years. Okay, so this isn't transferable to anywhere in the world, but there are places in the world where this is true, and North Belfast certainly is one. And intergroup conflict is, in these communities, the primary factor influencing mobility. Okay, so that's the thing that we can say with some confidence based on the work we've already done. And so what I want to do is create some kind of map, some kind of data set that helps me understand the kind of spatial patterns of that conflict. And effectively what I need is a territorial map, a map of the, for any given point in space, which community does that area belong to? And crucially, how strong is that belonging? And so that's the first step of this work. And I set out to make this using I think quite a common approach to lots of types of modelling, really, which is a Markov chain Monte Carlo Bayesian inference model, which for those who haven't come across these before is a lot more simple than the title suggests. So this is a relatively simple inference model, which means we take what we call a prior probability, which is our current understanding of the way things are. And then we iteratively add evidence to that, and that gives us a new understanding. And then that becomes our prior, and we add more evidence, gain a new understanding, and we're continually editing what we know in this iterative process. Now, in the context of what I'm doing here, we gathered some data to be able to try and undertake this activity for territory, effectively. So we started with the place people tend to start with this kind of thing with census data, because that lets us see what religion, what group people affiliate with, and from there we can get a good idea, a good starting position. It's lacking a lot of nuance, but it's a good position to start with. And then we can start adding in more evidence. So we collected GPS traces from 200 participants over 2 weeks. And we could see where people from different communities did and didn't go, and we could add that as evidence to our model. We could collect data from participatory GIS, 30 people mapped out in great detail exactly where these territorial boundaries were. And also we could take a survey, which we did. We have 500 people, we know exactly where they live, and we know how they self-define what community they identify with. And by using these 4 data sets, we started off with our census data. You can see on figure A in the top left. We added in our survey, B, participator GIS data in C, and our GPS data in D. And through the model, so the way this model works is it's inverse distance weighted squared. So for any point in space on a raster surface, we did it at 20-meter resolution, which reflects the kind of quality of the GPS more than anything. We ran a MCMC Bayesian inference model. So for every point in space, we have a figure for how Catholic or how Protestant the place is. And these data sets are shown in the green for Catholic and the orange for Protestant. Formally, what this actually is showing is the probability that the next person observed at that location will be a Catholic or a Protestant. And we are using that as a proxy for territory. So we're saying that if the next person is 99% likely to be a Catholic, then it's probably a Catholic area, and vice versa. I'm not saying this is a perfect model. You can see in the top left, in the very rural area where there's not much activity, you can still see remnants of the census zones. But I think that's okay. Firstly, this model is a dynamic representation. We can continue to add new evidence in here as we get it. We can deprecate old evidence and so on. So I think I'm quite happy with this in general. And crucially, I've presented something similar to this actually at GISRUK a few years ago, and we showed there that this type of approach really does capture far more detail that is missed by things like the census. So, areas that have changed over time since 2011, areas that suffer from the modified aerial unit problem, misclassification, and so on. So there's lots and lots of benefits of this approach. And this really is the crucial part of this work, is that we now have these models of Catholic and Protestant territory. And based upon that, we're going to take our GPS data, look at how people move in the context of those models, because people, as I say, their movements are being dictated by effectively the other group's territory. And I'm going to use that to create a simulation where we can model where people go and when empirically using our GPS data, and then move people through the model, and that'll allow us to test some hypotheses, test out interventions before they're put into place on the ground in these communities. Unlike David's, mine isn't a very pretty model. So here's a lovely 3D model and a video. I've decided not to go for the video. When the model runs for real, there is no visualization. So I can do a visualization for debugging purposes, and that's it. Obviously, this is only 100 agents. There are thousands when it really runs, but this runs on a high-performance computing cluster without any kind of visualization. But to just illustrate what's happening, Catholic and Protestants, green and orange agents are put in there in the kind of virtual environment, and they move around according to the empirical rules we've derived from the GPS data and the tolerance surfaces. And I'm just going to explain that a bit more now. So each agent has a number of parameters, and I've not listed every one here because that would get rather dry. I've just listed the key things. So our inputs really, we've got some GIS data, so we know where residential areas are. We know where roads and paths are. That's all come from OpenStreetMap. We take from the literature information about contact theory. So the effect size of positive and negative contact, the probability that two people meeting are going to have a contact. And if there is a contact, is that going to be positive or negative? The GPS data just on its own will give us things like people's walking speed, how many journeys per day they make, the destination types, where they go, and their mode of transport, and which will define how our agents move. And then that data will be analysed in conjunction with the territory data that we made in the Bayesian model. And that'll give us things like residential tolerance. How Protestant can an area get when this particular Catholic is going to still want to live in it? destination tolerance is the same thing, where they're going to go to, and the movement tolerance is the route they're going to take. So there might be somewhere that's perfectly acceptable to them in terms of destination, but they can't find an acceptable route to it, so they won't be able to go there, for example. And all of these things and several other parameters are created into probability distributions from which the values are drawn for every single agent as they're created, which is quite a normal approach for this type of analysis. Now, it's quite difficult to explain models like this, so I've gone for a pseudocode approach. So what happens basically is for every agent, they draw their parameters and pick a home location, which has to be within their residential tolerance, and it has to be within a residential area as well. And then basically, as the model moves, they just live their lives emulating the behavior that we've taken from the GPS data. So if they're due to, if they're at home, they'll decide, do I need to go out? Because they know how many journeys they need to make that day, they know how long they take, and so on. If they decide they do, they'll pick their destination, mode of travel, route, and so on.
I have 5 minutes.
Thank you. At a destination, they'll should they leave or should they be there for longer? If so, they'll make a route. And if they're journeying, they just move along their route to the next place. So they spend a lot of time at home, a bit of time at the destinations, and a bit of time journeying, just like our real people did according to the GPS data. And then after that, we calculate any contact that might have happened. So if two people were in the same place, did a contact happen? Was it positive or negative? And we update the thresholds that we calculated from the tolerance surfaces for that agent accordingly. And then we calculate some global segregation indices for those as well. And as you can see, this is all based on either the GPS data on its own, the GPS data along with those territory maps, or the literature in the case of the contact material. Now, when it comes to those segregation indices, the interesting thing is there's not been very much work at all into spatio-temporal measurements of segregation. Overwhelming majority of research in this area has been done into residential segregation, and where activity space segregation does happen, it still tends to be quite static and not very dynamic. So what we've taken actually is some information from a PhD thesis by John Palmer from 2013, who proposed some activity space measures of isolation and interaction. Now, these are classic measures of segregation. Massey and Denton proposed these in 1988 for residential segregation. And he's taken these, he's made some adjustments to them based in part on some work that Tumet et al. Did in 2012. And he's got these equations that are very straightforward for levels of interaction, which is basically a function of the number of people from your group that are with you compared to the total people that you meet. And conversely, the kind of partner to that is isolation, which is the same equation again, but this time for the number of people from the other group compared to the total people that you came across on your journeys. And these are calculated for every agent, for every step of the iteration. Goes into this, and then that gives us a value for isolation and for interaction for every step of the model, so we can see how that's changed over time. And therefore, if we put in interventions, if we change things, we can see what effect that has over time as the model progresses. And just to illustrate that point a bit more clearly here, so we take our input data, which is our Bayesian surfaces and our GPS data and so on. We then model a scenario, which could be, for example, we create a new shopping centre that's shared. Would that create enough contact to make a difference? Would it create contact at all? Or, if we did a big campaign and tried to do a wholesale reduction in a small area of prejudice, what would the outcome of that really be? And predicting what outcomes might be able to be achieved using these approaches by these measures of integration and isolation, which crucially links through to policy. We're working with numerous NGOs, community organisations, the Ministry of Justice and so on, in order to try and get this into use. And they've used quite a bit of our work already, and we're very excited to give this a go as well. And particularly around that question of, is there a tipping point? Is there a point at which there'll suddenly be a wholesale change in behaviour? And that's what I really want to discover in this model when we're able to run it, probably over the summer, and explore, what the implications of contact theory really are in a place like this. That's about all I have to say. I've got a list of the team members there. It's quite a large team from a GIS perspective. Duncan, Whyatt and Gemma Davies are the names you may recognise. There's a lot of open source data in here, particularly Mason, moving pandas, geopandas and so on. And if you do want to know more about the project, there's our website at belfastmobilityproject.org, or please do feel free to get in touch. My email's at the bottom. Thank you very much.
I just, by curiosity, you mentioned that you already did some work in this area. Thinking about the patterns, what you would expect in terms of this interaction and this contact between these different groups, according, for example, with this hypothesis that the contacts between different groups can reduce the segregation of the prejudice. By your knowledge of this area in Belfast, what do you expect to find?
I mean, I'm not trying to suggest that getting a bit of contact will suddenly solve all these decades-old problems. But what we are seeing, particularly amongst young people, is that sharing does happen in some situations, and that does change attitudes. The last paper I wrote about this was we found that what you might call non-places, so your supermarkets, your shopping malls, your McDonald's, your motorways, these kind of anonymous places where people don't have those kind of relationships with people in place. People find it's quite easy to share there. So I think it's about trying to understand how we can maybe use that and get people to, particularly the young, to try and integrate a bit, and just, reducing the levels of prejudice. And at the moment, of course, violence, because, that's really affecting people's lives. It's not something we want to see at all.
Did you map the uncertainty with Bayesian inference, and how would that influence the rest of the pipeline?
Yes, we certainly did. So as I said, every cell in that model is, so every kind of cell in the raster is its own model, and that has a distribution associated with it, and of course uncertainty. I'm still playing about with exactly how I'm going to propagate that through the model, and if you've got any suggestions, please do let me know. But yes, the model itself is going to run each scenario 1,000 times at least. At the moment, I'm thinking 1,000. So I imagine that the actual values in the surface as the model starts up will probably be drawn from that distribution rather than just using the mean value. So that would be one solution to that. But error propagation is something I'm by no means an expert in, and it's something we're certainly keen to make sure is built in there in a robust manner. So if there are any suggestions, please do get in touch.